This is an alternator, and this alternator needs a mount for the V-belt tensioner. And I will show you how we can optimize this structure for this function. We just import the geometry from a CATIA model. We can import from whatever CAD system, as you know. And when we have imported the part, each element, each part has been designed and defined for the mesh. And we will change the mesh of the design space to get a good result. So first step, we change the automatic created element sizes to use the element size we want to have. So we make smaller elements. As you can see here, we will use elements of a size of 5 millimeters. And all the other parts we will mesh with a default mesh defined by reading the model. Okay, a few seconds later we have the mesh, and we can go to the next steps. You can see the mesh is very good, very accurate. We have only good elements. The mesher is a unique developed function, so you can see it's really a good mesh. Next step, we will define the material we want to use for this design space, and this will be aluminium and not the default steel. Let's just change the color a bit so it looks a bit more like aluminium. Next step is we need to fix this part in a way that it does not use the stiffness from the alternator, but has its own stiffness as a result. And so we use the smooth virtual part, also known from Nastran as an RBE3 function, and we use it here on the points where the screw will fix this part. And we need another virtual part where we had to connect our load, to apply our loads, and we need a local coordinate system to define the point where the load is applied. We use a geometry to define a coordinate system, and we place the desired point at the end of this cylinder. Now we have all elements we need to define our load cases. Next step is, okay, now here you can see we will place now the handler of this virtual part exactly into the origin of this coordinate system. Now, next step is we had to connect all of these parts together, and all these parts can move against each other kinematic conditions. And we can do this automatically by a surface slider, and we define a search criteria, and we had not to worry about any degrees of freedom left free, because there's a virtual spring which is used on sliders if needed. We can change the definition of each connection just by clicking with the right mouse button and change it. There's no need to create new definitions. We can just change it. As you can see here, I have just changed the sliders to a fixed condition. Okay, now next step is we had to define a load case. In this case it's a static load case, and we apply the load at the virtual part here as a force in the direction of the coordinate system, Z direction of the coordinate system. It's approximately 1000 newtons we had to apply here. And on the other side we fix the complete assembly in the center of this virtual part, so it remains flexible on the outside. Now we had to define our topology optimization conditions. We use the load case we have defined, and we use a geometry as design space, and we limit the number of iterations to 50 in case if there are some problems, then the calculation run will stop automatically. Some of the holes we want to keep, so we define faces which should remain in the result. We just click on it, and these faces are locked from optimization. It will be kept, and we will have it in the geometry at the end. Okay, now everything is defined for an optimization, and now we can use a special function in CATOPO to speed up the calculation time by a factor of about 3. First, we switch off the high accuracy elements. Topology optimization only needs relative values, not absolute values, and we can use a solver on a local computer like here, or we can use it on a server on an external computer. Okay, let's start the calculation run, and the calculation will take, let's say, approximately between 15 and 25 iterations. And during the calculation run, we can analyze what happens during this optimization run. One way is just to look on the log window, like you can see, here's this black window. The other is we can visualize the convergence condition by creating a 2D plot, and so we can see if the result is really converging, and if it's not converging, we can interrupt it at any time and look what's wrong. Okay, we have several iterations created now, and let's see what happens. And here you can see that the result becomes something, it looks nice here. So let's go on, and let's start a 2D plotting to show the convergence not only in numbers like here on the screen, but also in a curve. And so we can switch forward and backward through our windows, looking on the log window, looking on the 2D window, and in the meanwhile also importing an intermediate result, looking at it. And so we have different ways to check if our calculation run is really on the right way. And when you look at it, we can roll through all the iterations and see how it changes from step to step. And a few minutes later, we will have the final result. Let's just wait for this final result, and then let's look what we got from it. Okay, we have now about 20 iterations. It's not at the end now, it's nearly at the end. The curve showing the convergence is flat now, and it's only a question of a few minutes that it will be completed. And as you can see here, this runs in a lifetime on a notebook. It's a Lenovo W520. So if you want to check the power of this computer, you can see it's just an average computer, nothing special, and we can do this in lifetime on a normal computer. And when we have the first when we have reached the convergence criteria, you can see a green line that shows that we have reached the convergence criteria first time. Now 2 additional iterations will be done to be sure that there's no oscillating result. And after this is completed, we have our final result, and as you can see, it's only a few minutes for this optimization. It's less than 300 seconds, so it's less than 5 minutes for this complete solution. Let's import the final result, and as you can see, it's not a big difference between iteration 20 and the following iterations. Next step is we cut away the weak material, and we can do this, we can cut through the elements. This is a very special function in CATOPO to show a very smooth result without smoothing function. And the result you will see now is the original result without any additional smoothing. So you can see it's a really good result. And the very interesting next step is we can analyze this structure without creating it in the CAD system. We can just say compute, and a few seconds later we will have this result on the screen, so we can check if we did it right. You see it's only a few seconds, and then we have this result on the screen. Here you can see it's less than 10 seconds to create this result. And this result is stress, it's displacement, and it's in high accuracy. Due to the reason that we have used this very special tetra element, which has 6 degrees of freedom per node. This is a unique element in CATOPO, which speeds up calculation time up to 15 times. That's the reason why we can do it in this short time. And now I will show you another nice feature. We will create an additional load case. We have not used this load case for the optimization. We only want to check the result on it. This is a load case for eigenvalues, and we will analyze our newfound shape for eigenvalues without having this load case used for the optimization itself. We just create a new load case, and now we use this new load case on our new shape, and we will do an eigenvalue analysis. Also, we will do it in live time here. It's approximately between, let's say, 40 and 50 seconds, I expect. And after that, we can analyze the eigenvalues. This is a very neat feature in CATOPO, that you can use load cases for the optimization and load cases for the verification absolutely independently. And you can also use multiple bodies for optimization. You can use multiple load cases, and you can define the load cases in a way that you can take into account the number of cycles used. So lifetime you can define in this optimization. You see, it's about 40 seconds, and now we have our eigenvalues calculated on our new shape. And here I have done it for 10 eigenvalues, just to show that it's really fast. Okay, so a very, very short calculation time, very easy to use, and a way to find the best shape in an absolutely very short time. Okay, so if you like this, come to us and we will show you, and we give you a test license, and we can give you some education, and you can use this software for your purposes. Thank you for your attention.